Okay, I guess we can start, and if needed, we'll have the missing speaker just reordered to be when they arrive. Does that make sense? Okay. So I guess welcome everyone to the session A2 of this virtually held ICALP. I think what we'll do is we will go with the order that is currently written on the Slack channel. So we'll have each speaker do a very short sort of summary of their presentation, and then we'll take questions.
I can't hear you now, and I'm not sure if I'm supposed to begin.
Does everyone else hear me?
Sure
or?
I can hear you, yes.
So I will enter again.
Another thing is maybe we can mute everyone so that only the speaker can, because we hear also typing on a keyboard, which I think. Okay. So yeah. So the first paper, the first presentation is a water filling Primal-Dual algorithm for approximating nonlinear covering problems. Andreas, would you like to share your screen and give us a short presentation, short summary? Andreas, are you here? Can people hear me?
Yes, I can hear you.
Okay.
So I think he was the one saying that he cannot hear us anymore.
Okay, I didn't realize who was saying that. So let's change the order a bit. Because I don't know if you can hear me. Andreas Feldbaum, can you hear us? Okay, so let's start with the next one. So we'll start with an optimal algorithm for online multiple knapsack. And sorry for probably going to pronounce this in a wrong way. Maciej Passoul, are you here?
Yes, I'm here and I'm ready to share my screen.
Great. You can also, if you have a camera and you want people to see you, you're welcome to.
Not really. Do you see my screen?
Yes, we see your screen.
Yeah, very nice. Okay, hi, I'm Maciej Passoul from University of Vienna. This talk is about an optimal algorithm for online multiple knapsack. Online knapsack is a classic online resource allocation problem. In this problem, we are given a fixed number of identical containers of capacity 1. Then a stream of items of various sizes arrive one by one. Upon seeing an item, we either reject it or accept it into one of our knapsacks. While doing so, we must obey the capacities of our knapsacks. The goal is to maximize the total size of accepted items. We present an optimal algorithm for this problem called the rising threshold algorithm. Its competitive ratio is 1 divided by natural logarithm of 2e, which is approximately 0.59. Our algorithm is deterministic and its competitive ratio matches the randomized lower bound. I'll quickly recall what the rising threshold algorithm does for items of size larger than half. We assign each knapsack a threshold. When an item arrives, we attempt to put it in the leftmost empty bucket. If it doesn't fit there, we reject it. Just like this, the items arrive and we place them on the leftmost empty bucket unless it's smaller than the red threshold, and then we reject it. And we continue. To determine thresholds, we use an exponential function f, given on the slide. Just like this. Function f has some unique properties that guarantee the optimality of the algorithm. Namely, the area under the blue line, the ratio of the green area to the area below the blue line is exactly our competitive ratio for each point on the curve. This quickly sums up the analysis for rising threshold algorithm when it only receives items larger than half. For other items, read the paper. Okay, thank you.
Thank you. Any questions? I guess we're not too many people, so you're welcome to simply unmute yourself if you have a question and simply ask.
Yeah, hi. So do you hear me?
Yes, we hear.
Yes, so I do have a question. So when I listened to the video, I had the impression that, so as I remember, your approach works for unweighted cases, right? And for weighted cases, for the weighted instances, it is much harder to deal with that. So could you tell me what are the main difficulties to actually deal with a weighted case?
So basically in the deterministic case, it's very easy to produce an instance where your competitive ratio is unbounded. For example, let's consider a sequence of 2 items, and let's say that you have only one knapsack. If the first item has really small weight, which means really small profit, and the other has large profit, then if you only accept the first one, then the adversary gives you another item that you cannot take, and the optimal strategy is to take only this one. And if you don't take the item, then the adversary ends the sequence immediately, and you don't have any gain at all. So this is a very simple instance. However, there are also results that in the randomized setting, this is also non-competitive. I'm not really aware of the details of the construction. However, I know that the problem is there is a lower bound that gives you that you can be arbitrarily bad.
Yeah, thanks.
We can take more questions.
Hello, can you hear me?
Yes.
Hi. Well, first of all, thanks a lot for the talk. I found it really, really nice. So I wanted to ask you about variants of the problem, and like maybe similar to Tobias' question. Like specifically, I would like to, or I would be interested, given this very strong lower bounds that you just mentioned, especially for the weighted case. Do you know anything? What happens if you, for example, allow some relaxation of the problem? Maybe you are allowed to reassign some items over time in a limited way, and then maybe you can study a trade-off between reassignment and competitive ratio. Are you aware of any work on this direction?
Yes, I'm aware of a survey on online knapsack variants by Sigan and Yesh from TOCS 2016. I will put the link to the Slack for this talk, and there's a nice table that sums up all the results for variants, relaxed ones, the proportional or weighted cases, with the possibility of removal and without the possibility of removal. And this is a great source of information that will point you in other directions.
Okay, thanks a lot.
Any additional questions? Okay, thank you very much.
Thanks a lot.
So we'll now move to the next talk. We'll do A to C. So this is a paper on solving non-commutative weighted Edmonds problem, and Taihei Oki. We have him here. Can you share your screen? Maybe the previous speaker needs to first unshare the previous screen.
Sorry, I didn't know that. And
I didn't either. Just the stop sharing button somewhere. Great.
Oh, probably here.
Can you try now, please, Taihei? Great. Great, go ahead.
Okay, thank you for the introduction. My paper title is on solving non-commutative weighted Edmonds problem. So this is a summary of my work. I proposed a simple polynomial time reduction of commutative or non-commutative weighted Edmonds problem to commutative or non-commutative unweighted Edmonds problem. To explain my work, I need to introduce what the Edmonds problem is. Edmonds problem is a very simple problem. We are given n+1 matrices over some field K, and we want to compute the rank of a matrix B0 plus B1 x1 plus blah 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 bn times xn. Here, x1 to xn are commutative variables. Indeed, this rank computation problem is known to be a generalization of bipartite matching, linear measured intersection, and linear measured parity problems. So to compute the rank, it suffices to randomly substitute a random number into x1 to xn. Then we can compute the rank just by Gaussian elimination. However, deterministic polynomial term algorithm is not known. The weighted version of this problem is as follows. We are given n+1 polynomial matrix instead of constant matrices. So with B0, B1 to Bm are now matrices whose each element is polynomial in S over a field K. Then we want to compute the degree in S of the determinant of B0 plus B1 x1 plus blah blah Bn times xn. Indeed, this problem is known to be a generalization of weighted bipartite matching and weighted linear measured intersection and so on. And my result is construction of a polynomial time reduction of this weighted Edmonds problem to unweighted Edmonds problem. Yeah, so this is a summary again. And the feature of my reduction is it can be applied to non-commutative version of weighted Edmonds problem. A non-commutative weighted Edmonds problem is just a rank computation problem in which variables x1 to xm are regarded as pairwise non-commutative variables. Then the non-commutative Edmonds problem is known to be the deterministic polynomial time solvable. Then by using my reduction scheme, we can devise a deterministic polynomial time algorithm for non-commutative weighted Edmonds problem. That's all. Thank you.
Thank you very much. Questions?
Yes, I do have a question. So is there actually also some connection to general matchings? Or is it really the connection is only to bipartite matchings?
In general matching, the number of maximum size of a general graph can be obtained as the rank of the TAT matrix. So there are connection, but my reduction does not reduce the weighted bipartite matching problem to unweighted bipartite matching problem. So it is so if we are given an instance of weighted bipartite matching, then my algorithm reduces it to unweighted Edmonds problem, not the unweighted bipartite matching problem. This is the same for general matching. Yeah.
Yes.
Is my answer okay?
Thank you very much.
Thank you for the question.
Do we have additional questions?
So I had one quick question also. Can you hear me?
Yes, go ahead.
Yes.
Please.
So can you say just briefly about your reduction in the sense that does it work by just changing the instance once and applying the unweighted algorithm, or you have to repeatedly, let's say, do binary search or something?
So binary search.
Not binary, I mean, that doesn't matter. I mean, is it that you just take the instance and you change it into another instance of, you take the weighted instance and turn it into an unweighted instance and then you solve the unweighted problem? Or you have to run the unweighted algorithm once, then based on that, adaptively decide to create another instance and continue like that?
My reduction is just not the Turing reduction, but the one-to-many reduction. That is given an instance of a weighted Edmonds problem, we can compute the degree of the determinant just by computing the rank of a matrix just once.
I see. Okay, got it. Thanks.
Yeah.
We have time for maybe one more question, if there is any.
I have a question. I have actually two questions. So one is, can we see this as, in context of bipartite matching, can we see this as reduction from weighted bipartite matching to 0-1 weights?
0-1 weight.
So I mean, weighted bipartite matching to bipartite matching with only weights which are 0 or 1.
My algorithm does not reduce the weighted bipartite matching to unweighted bipartite matching.
Okay.
Yeah. So okay. My algorithm reduces weighted bipartite matching to some instance of unweighted Edmonds problem, but unfortunately, the reduced instance does not correspond to unweighted bipartite matching.
Okay. So another question is, are there any combinatorial problems which are instances of non-commutative weighted Edmonds problem?
It's a very interesting question. As far as I know, the corresponding combinatorial optimization problem is just known for only for commutative program.
Okay.
Yeah.
Okay. Thank you.
Thank you very much.
Additional questions, anyone? Okay, thanks a lot for the presentation.
Thank you.
So what we're going to do now is go back to paper A2A. So Andres, can you share your screen with us?
Yes, can you hear me well?
Yes, we hear you well. So the paper is a water-filling Primal-Dual algorithm for approximating nonlinear covering problems. And Andres Sjöblom is presenting.
Okay, can you see my screen now?
Yes, go ahead. Thanks.
Okay, thank you. So yeah, well, thank you for attending this Q&A session. I'm presenting this paper that's made together with Ignacio Morales and Jose Verchay, who's also connected now. What we are doing is using an algorithm that can be interpreted as a water-filling algorithm to approximate some nonlinear extensions for some classical covering problems. So to explain or to recall better what do I mean with these extensions, I will explain it with the nonlinear knapsack cover. So in the classical knapsack cover, we have n items, and each item has a cost and a capacity, and you must select some subset of items in order to cover all the demand D, but with minimum cost. In this case, we are considering that capacities and costs are not fixed, but are determined by a function that is non-decreasing, meaning that you can choose whatever capacity you want, but each capacity has an associated cost that is non-decreasing. But we are not putting any extra hypothesis on F, so it can be non-linear, non-convex, it can have not necessarily continuous, it can have convex regions and concave regions, and etc. So the linear program is this one. We need to minimize the sum of the cost of the selected quantities that we are taking from each item. Of course, we have to take just positive quantities from each item, and we must cover all the required demand again. And these are examples of the cost functions that we might consider. This is a nonlinear and non-convex problem because F can be anything. And our two main results are these two theorems. So for the nonlinear knapsack cover, we can admit a polynomial time Primal-Dual algorithm that gives a 2 plus epsilon approximation. So with the classical knapsack cover inequalities with a Primal-Dual scheme, you obtain a 2 approximation. So we are just losing epsilon because we are using these arbitrary non-decreasing functions. And we also studied the unsplittable flow path cover on a path. In this case, the best known algorithm gives a 4 approximation, and with our Primal-Dual approach, we again only lose epsilon when we consider any non-decreasing function instead of fixed cost and capacities. So this is the recalling of our paper, and if you have questions and answers, me and Jose will be happy to answer them.
Great. Are there any questions? Thank you, Andres. Maybe you can either put back your slides or
Yes,
finish the sharing. Otherwise, we see. Any questions to Andres?
So I have actually a question for that. So thanks for the beautiful presentation. I really enjoyed it, actually. I really enjoyed your result. And it seems to be very general. So did you actually try to apply it also to other problems?
We have thought about that because, yes, the algorithm itself seems quite, I mean, it has we like it also. Thank you for the comment, because it has a really clear interpretation of how the water filling is telling you which item you should increase marginally. So we think it might have other problems, but we have not thought directly on any of them. We did put some thinking on if you are considering the sending flow over a graph, over a tree, for instance. But when you have a hierarchy over the arcs, there is some problem of how you chain the cost functions of the preceding arc to the following. So in that case, at least for now, we have not been able to figure it out. But there might be other problems without this hierarchy between arcs that we also expect this could be used there, but we have not analyzed it yet.
So maybe I can complement a little bit. In principle, the nice thing about this set of inequalities is that it can be used for any problem where regular knapsack cover inequalities are used, right? So it's just like you can generalize all of these problems where this well-known set of inequalities are used, which are many. We haven't really thought about it that precisely. It's also not clear. I mean, our formulation seems complicated when you see it on the first hand. You can get a simpler formulation which is as strong in pseudo-polynomial time, actually, or pseudo-polynomial size. But the problem is that it does not admit like such a nice Primal-Dual interpretation of like this water filling algorithm. So this also is unclear whether any of these other problems which do not admit a Primal-Dual algorithm in the classical problem will be you can improve their or get a nice result out of this set of inequalities in a Primal-Dual sense. So, yeah.
Yeah, thanks. That is really interesting.
Thank you.
Are there more questions? Okay, thanks a lot.
Thank you.
We'll now move to A to D. So Noor, you're welcome to share your screen. This is optimal streaming. Yes, this is optimal streaming algorithms for submodal maximization with cardinality constraints.
Yeah. Okay. Hello. Hi, everybody. As he said, this paper is about submodular functions, and it's joint authored by Alina Eme, Moran Feldman, Hui Lowen, and Andrew Sa, who you heard in the recorded presentation. Actually, submodular functions are set functions, and they capture the notion of diminishing returns, which means that for every new element that we want to add to an existing solution, we see that as the solution grows, this element actually contributes less and less. A submodular function is also called monotone if a new element can only increase its value. So what we did in the algorithm, in the two algorithms that we presented in the paper, is that we showed that if we take portions of elements, or we partite the whole data in such a way that we post-process the data afterwards, after the algorithm, the elements that we took to our solutions, their value is large. It is proportional to the optimal solution, and actually the elements that we didn't take are of small value. If we look at previous works, we see that for the monotone settings, we have an almost optimal algorithm from 2014, and we see that you can't really get more than half in the string model. We see that the state-of-the-art algorithm got an approximation ratio of 0.1715, and our two algorithms that they will differ in the methods, because one is more random. It uses more randomized processes, and the other can be actually made deterministic. And it's using an extension of the submodular function called the multilinear extension. We see that if we post-process the algorithm with the state-of-the-art offline algorithm, we get a 0.2779 in approximation ratio. And actually, we can, if we have a small size solution, we can actually post-process in exponential time and get an almost optimal approximation ratio for this problem. And that's it, I think. Thank you.
Thank you, Noor. Questions? Anyone?
Yeah, I have a question again, actually.
Hi.
Oh, hi. So as I remember, you used randomized rounding techniques like pipette rounding, but it was not LP based, right? But is there some strong connection to linear programming, because these would be techniques usually used for rounding linear programs, right?
What is the question again?
So you're pipette rounding all these techniques.
Yeah.
So these are techniques that often are used in the context of rounding linear programming relaxations. So is there a connection to your paper, because you did a different type of randomized analysis, right?
Actually, we use the pipette rounding because our second algorithm takes only parts of the solution, only parts of the items for the solution, and we need to get we need to get a set of items, a subset of all of the items that we considered and took parts of this item and parts of that item. We want to get a set of size at most k, and we can actually hold more than size k if we add a p portion of every element. We hold k over p elements, and we want to take a subset of these elements of size at most k. We do that using these techniques, so we won't lose any value. We will get at least as much value as the multilinear extension gives us.
Okay.
Okay.
Additional questions?
Yeah, so I had also two questions. Can you hear me now?
Yeah.
Okay, good. So one is that, is the space of your algorithm just order k, or it's some polynomial in k?
Do you
K being the cardinality constraint.
Yeah. Do you ask about the space complexity?
Yes.
It's on the order of k log k. It's actually semi-streaming algorithm because of that.
Okay. And what about dependence on epsilon? Is it polynomial or exponential?
Oh, it's polynomial in epsilon. Yeah.
So this was one, and the other is that you're getting a solution that you're saying contains a half approximation of the optimal solution, and then you're running another algorithm. So if I want to run in polynomial time, is your guarantee the type that you have an half optimal solution and then you run a polynomial time algorithm on top of that?
Okay, I understand the question now. What happens is that the algorithm takes a K over P elements, and then it post-process the data that it has. So if your K is relatively small and you can run this offline algorithm exponentially, so you can find the optimal solution for this subset of items. So it will be exponential in the K over P elements. But if you use the state-of-the-art deterministic and polynomial time, not deterministic, sorry. If you use the state-of-the-art polynomial time algorithm for this post-processing, you will get that 0.2779 approximation that we guarantee.
I see. And is it, yeah, so I was probably asking that, is it clear that you have to lose exactly, the instances that you get at the end has some specific structure. They are not arbitrary instances, I assume. So is it clear that you have to lose all the approximation factor of the state-of-the-art algorithm? Or if you analyze it in a white box manner, you actually get something even better?
With the approximation ratio we got depends on the offline algorithm, actually. All of the calculation of the approximation ratio depends on it. And as the algorithms for the offline problem will improve, if they will improve, this approximation ratio will improve with them. But our analysis use the approximation ratio alpha.
Nice. Okay, thanks.
You're welcome.
Any additional questions? Okay, thank you, Noah.
Thank you.
I don't see here any of the speakers for A to E, so we'll go to A to F. So Rohit, you're welcome to share your screen. Great. This is a linearly representable submodal of functions, an algebraic algorithm for minimization.
Hi, can you see my screen?
Yes.
Okay, so this is a work on submodular functions. So Naur already defined what submodular functions are, so I will not go into the definition. So in this work, what we do is we define a new class of submodular functions, which we call as linearly representable submodular functions. So the motivation behind this definition somewhat comes from linearly representable metroids. And our main result is that for these kind of submodular functions, we give an algebraic algorithm for minimization. Let me go into the definition of linearly representable submodular functions. So the basic building block for this definition is comes from this rank function corresponding to a family of subspaces. So suppose you have a family of subspaces. So say each you have a ground set capital E, and for each element of the ground set, you have a corresponding subspace. And now you can define its rank function, which is which assigns a number to every subset of your ground set. And this number is basically, if you take a subset S, you collect all the corresponding subspaces, take their union, take the span, and consider the dimension. So that is the rank function for this family. And it turns out that this rank function is submodular. So this will be a basic building block for our definition. Now note that this rank function is a monotone function in the sense that if you add more elements, that will add more subspaces and it will only increase your rank, right? So the way we define a linearly representable submodular functions is, suppose you have two families of subspaces, let's say V1 and V2. And then for any subset S for the ground set, for any subset S of the ground set, you define the function to be R1 of S plus R2 of S complement, where R1 is the rank function for the first family and R2 is the rank function for the second family of subspaces. So the point of this definition is that now you get a non-monotone function, because R1 of S is increasing and R2 of S is a decreasing function. You get a non-monotone function, and that makes it interesting. So this is what we refer to as linearly representable submodular function. So what are some interesting examples? So the graph cut function, directed graph cut function, hypergraph cut function, they all fall into this class of submodular functions. Moreover, you can define functions in graphs involving degrees or in the cardinality of the influencing set. So all these functions will fall into this class. Besides this, there is this weighted rank function corresponding to linear metroids, which will also fall into this class. And then there is a coverage function. And more interestingly, if you take any combination of them using this using this kind of equation, that you apply one function on the set S and the other function on the set S complement, and still it gives you a linearly representable submodular function. So as I said, our main result is that for this class of submodular functions, we give a minimization algorithm, which is algebraic. So algebraic in the sense that the minimization question is simply reduced to a matrix rank computation, and our reduction is randomized, and that's why we get a randomized NC algorithm. So NC here means a parallel algorithm. Moreover, we can also de-randomize our algorithm so that it doesn't need to use too many random bits. So that's our main result. And as applications, so there are many combinatorial problems which reduce to minimizing these kind of submodular functions. So for example, maximum bipartite matching, linear metroid intersection, max flow min cut. So all these problems are special instances of these minimizing these kind of submodular functions. But these problems already had algebraic algorithms, and our algebraic algorithm in a sense is generalizing those algorithms. But we also have some new applications of combinatorial problems. So there are these two combinatorial problems called covering by K arborescences, and another one called packing of branchings in directed graphs. So these two problems are known to reducible to submodular minimization. What we show is that they in fact reduce to linearly representable submodular functions, and that's why we get such parallel algorithms for these two problems. As a nice byproduct, we also get an algebraic proof for this min-max relation, which is known for submodular functions. So that's all I will say in this summary.
Thank you. Questions?
So one quick question here. Can you bound the query complexity of the submodular function to be something small here also, or is just some large polynomial? You know, there is this line of work trying to minimize the query complexity of submodular minimization, and how many times you. But in that context, is it, and many of the examples you've shown, we know how to solve them with query complexity less than n square.
Okay. So we have not thought about this, but yeah, this is potentially a good research direction.
Nice. Okay, thanks.
Any additional questions? Okay, thank you very much, Rohit.
Yeah, thank you.
Any chance that any of the speakers of A2E joined us meanwhile? I don't see them. Okay, so I guess we can pose questions to them on the Slack channel. And I'd like to thank all the speakers and all the participants of this session. Thanks to you very much. And I think this concludes our session.
Thank you.
Thanks, everyone.
Thanks.